Hello, everyone. So today, I'm going to talk about how we use partial memorization for accelerating mostly deterministic code regions. So to begin with, as you may know, memorization is a powerful optimization for repeated and deterministic computations. For example, if the first instance of your function returns bar if the argument is full, so basically for future executions of the same function, you can remember that by returning bar directly without re-executing the function if the argument is still full. This is useful in many use cases. For example, static web page, or you can use makefile to avoid recompilation if you don't change your source files. If your application startup is deterministic, then you can always restore from a checkpoint taken at the end of the startup operation, just like Android Zygo does. So if we want to provide this feature in a generic way at the operating system level, what should we do? Well, given such a code region from some arbitrary binaries, we will first figure out what output is generated from the first instance of this code region. Then we'll remember those output and then compare the memory and register state between the region start and region ends to figure out all the memory differences made by this code region. Store that as a state diff. The next time you have the same code region, we simply regenerate the same output, apply the state diff, so you can safely jump to the end of this code region for acceleration. This works pretty well for computations that are mostly the same. Exactly the same. But what if they are mostly the same? Like there are some small differences across different executions. For example, what if your web page displays same content except different usernames? So what if you change one line of in your source code? What if your application startup raised 9 deterministic inputs like the current time? So in those cases, memorization are incorrect. So basically you have to fall back to re-execution of the entire code region. Of course, you can develop some handcrafted optimizations for each of these scenarios, but that's very complicated and not generic. So in ShortCut, we try to provide a generic way for solving this problem by partial memorization. The observation is that there is only a small set of things that could differ from run to run for this code region. So we can logically separate this code region by, with static components where things don't change and they tend to generate same result, and a dynamic component where things could differ and they could generate different result on different executions. The static component can still be memorized by the traditional technique I mentioned early on, and we store the result in the state diff. Later on, we first apply the state diff and then re-execute everything from the dynamic components to make sure we have the new 9 deterministic inputs, generate the output, and what's more, we patch the memory locations that will not be able to be captured by the static state diff. At this point, we actually reach an equivalent program state as the original execution. Afterwards, we can jump to the end of the code region. So if this dynamic component is much smaller than the original code region, then we can accelerate this code region. So in this talk, I will refer to this dynamic component as executable slice. So you may wonder, how do we generate those slices at the first place? Well, we always start from 9 deterministic inputs and use information flow tracking or taint tracking to include all x86 instructions affected by those inputs. In this example, the input might be the current time. Then we figure out all the instructions affected and the output that could be affected. So you may also ask, like, what kind of input should we consider? You can be super conservative, say that every possible input from the memory, every input from system call should be considered. But that could easily end up like tainting almost all instructions in this code region. And the slice will be super large, and there's no benefit for acceleration. Plus, to be conservative, you have to consider all execution passes for this code region. That implies static analysis, which is not that scalable for large code regions with billions of instructions. That's what we target for. So instead of considering all possible input, we actually make assumptions. We use profiling to tell us what input or control flow or data flow could change. For example, the input, like we can check that input, the memory input and system call input still have the same value, or the control flow still take the same branch, or data flow still read or write to the same memory location. So our slice will embed all those assumptions, which we call predicates, inside of it. And it will verify those assumptions as it executes. The benefit for using predicates actually makes the slice much smaller, because slice only need to include instructions affected by things that are likely to change. And predicates will check all those inputs that are unlikely to change. This also implies we can use dynamic analysis because we don't have to consider all possible execution passes, only consider those those passes that are likely to happen. So dynamic analysis would be more scalable for large code regions. So the most important thing about slice is that it should be self-verifying. That means if every predicate in the slice succeed, we have a valid slice execution and we end up in a valid memory state. Otherwise, if any predicate fails, we basically have a bad slice execution and the memory state is undefined. So you can try to avoid those bad slice executions at the first place if you try to check all the predicates before you run the slice. But that's not very feasible because for some input, it's not yet known before you actually run the slice, just like the current time. If the slice has some branches, it's harder to predict which one it will take millions of instructions beforehand. So instead of like checking all predicates all at once before we run the slice, we actually check them as we execute the slice. So the problem, it solves some problem, but the other problem is, what if a predicate in the middle fails? That basically means we are left in a weird memory state. So in those cases, we will try to rely on rollback recovery. So before we run a slice, we take a checkpoint. If any predicate fails, we will roll back to this checkpoint and then execute the original execution from this checkpoint. So in this case, we have to make sure all the output will be consistent with the external world. So those details will be discussed in the paper instead. So the combination of these two ideas, like predicated slice and rollback recovery, makes this partial memorization feasible. From the high level, ShortCut will always start from profiling. We will do offline analysis to figure out what inputs, what control flow or data flows are likely to change. And then using those profiling information, we do offline slice generation. Afterwards, if the same code region is invoked, again, we will try to accelerate by loading the state diff and run the slice. If there is some failures, the failure information will be gathered and sent back to the profiler so that we can make better assumptions later on and also make the slice more generic to tolerate those failures we have seen. So I will first talk about some details about the profiling. So currently, ShortCut will profile by pairwise comparison of executions. So anytime we saw some divergence in the input or control flow or data flow, we will add those divergence into our profiling result. That means we will assume they are likely to change in the future executions of this code region. That's a very simple heuristic that works well right now, but we think that probably need more improvement in the later. After this information is gathered, we will start to use Intel pin to generate those slices. Imagine that profiler tells us that X is likely to be 1, but Y has multiple values from the profiling set. Therefore, we can add a predicate for X being equal 1 and tempt Y. Afterwards, instructions only affected by X don't have to go into the slice, because their result can be minimized. Instructions affected by Y, however, should go into the slice because their values are affected by Y. In this step, we also replace predicated values like X with some constant. So now we become tainted. For external outputs, we should include them into the slice because slice execution should regenerate them. So what if some tainted values or some input affect conditions of the control flow? For example, profilers tell us Y could change, but it's unlikely to be 0. That basically implies this control flow will always take this one of the branch. In that case, we put a predicate about the condition of the control flow, and also we don't tend C because the value of C can be minimized. What if a profiler later on tells us that Y can be 0 actually? So in those cases, both branches would be taken. The slice will now include both branches into it to tolerate this kind of divergence. Now, the value of C is undetermined, so we have to also add C to the taint set. Similarly, some input could affect data flows. For example, the Y can affect this array index. So in that case, we will first check the memory locations or access for future executions will still be within expected range. Plus, we will check the memory values at those locations. Finally, because C's value is undetermined, we still taint it as a result. Okay, now with the slice, we can actually try to accelerate for the next execution. As I said, we will start from checkpointing with a fork. Then we'll load the state diff, apply it, and then load the slice, run the slice. If every predicate succeeds in this slice execution, we can safely jump to the end of the code region. If any predicate fails, we will trigger transparent rollback recovery, so there is no impact on the user side. Those failure information is valuable for us, so I can actually use those information to incrementally refine our assumptions and refine our slice. So those details about the recovery, refinement, or generation will be discussed in the paper. So now let's look at how ShortCut, what's the evaluation result for ShortCut. So specifically, we consider two questions, like what's the benefit for it to accelerate mostly deterministic code regions, and what's the cost for predicate failures. In the evaluation, we have 3 benchmarks. The first benchmark is 2 workloads for 2 websites. So for both workloads, our ShortCut is able to improve throughput by more than 4 times. And it significantly reduces the media latency and the tail latency. Of course, we can make some bad assumptions, so the predicate could fail for some executions. In those cases, this graph shows the cost for recovery. Specifically, we consider 2 extreme scenarios. What if the first predicate in the slice fails, and what if the last predicate fails in the slice? that are represented as early failure and late failure in this graph. In both cases, there is some overhead for recovery. But the overhead is pretty small, so if you consider all the executions we have, predicates only need to succeed about a quarter of the time for us to break even. Similarly, we have a great speed-up result for application startups and compilations. The break-even point are even better in those two benchmarks. In conclusion, we try to provide generic partial memorization at the operating system level. The idea becomes feasible because we combine the predicated slice and rollback recovery. So with that, I will conclude my talk and happy to take any questions.
Tom Ping from UMass Amherst. So I have a question about this. So great talk first. Yeah. So can you support a multi-threaded program, or can you imagine how to support that if not?
Yeah, actually, currently we support multi-threaded program by basically we remember the thread scheduling decisions for the first instance and try to replay the same thread scheduling for future executions.
Hi, Arsenij Zastronych, PFL. Very inspiring work, by the way. I have just a clarification question on the slide 20. You've put on the slide number 20. You've put predicate for the values in the array.
Yeah.
And then you still consider the result of the array lookup as a talented variable. Why do you need those predicates?
Oh, you mean the predicates for like A0, A1?
Yes.
Okay. So at this point, like we don't know which location C will access, right? So those location values could be tainted by some other instructions. We want to avoid those cases. Like for example, for the future instance of the same region, like A0 might be modified by another instruction. C has a different value than expected. We specifically want to avoid those situations.
Could you just give a quick example of what would happen if one of those checks were not there and it was not true, like
yeah,
A0
sure.
is not 12 but 11?
Yeah, sure. For example, the A0 is might be some absolute memory locations. So it could be modified by some previous instruction in the slice, right? There's no restriction about that, right? So like at this point, we don't want to read these kind of wrong values from this location.
Okay, let's speak offline.
Yeah, sure.
Okay, let's thank our speaker.